Probably I should introduce the speaker first. Hey everyone, good morning, good evening, good afternoon, wherever you are. Welcome to the workshop on game theory in blockchain. And we're happy to have the first talk on scaling on-chain asset exchanges via our Debreu exchange markets by Geoffrey. Go ahead.
Hi, yeah, thanks. I'm Jeff Ramsire, and I'm going to talk about scaling on-chain asset exchanges via Debreu exchange markets. This is joint work with my advisors, Ashish Goel and David Mazieres. So that's a long title. So let's start by unpacking that title. So what's an asset exchange? For this talk, an asset exchange is some place where many different agents can come together to post offers to, say, buy and sell different assets. The role of the exchange is to match parties who agree on terms of trade. For this talk, all assets will be divisible and fungible. You should think of currencies or Bitcoin or Ethereum as the motivating examples here. Okay, so that's an asset exchange. What makes an asset exchange run on a blockchain different from an asset exchange run in a centralized context? And the main difficulty with running an asset exchange on a blockchain stems from the fact that in any large set of offers to buy and sell different assets, there are usually many ways to match buyers and sellers. For example, in a market trading dollars for euros, there are probably going to be many people selling dollars at roughly the same price, and there are probably going to be many people buying dollars at roughly the same prices. And so, in general, we could probably match most buyers with most sellers, and everyone would be happy. However, the exact details of who gets how much money depend precisely on how we match buyers and sellers. So, for example, right here, we have two people on the left offering to sell $1 and two people on the right offering to buy $1 for slightly different rates. And either person on the left could be matched with either person on the right, but one of the people on the left is going to get paid 1.01 euros, but while the other one's only going to get paid €1. And so depending on how we match agents on the left with agents on the right, there's a slight difference of 0.01 euros between the resulting balances of the traders. Okay, so now if we ran an asset exchange in a traditional centralized context, well, the exchange would get a set of orders, and it could just output any one of these potential matchings, essentially at random or via a non-deterministic process. But running an asset exchange on a blockchain means that we need to have the behavior of every node be somehow replicable. In particular, if one node matches offer A with offer B, then every other node also has to match offer A with offer B. If some node starts matching offer A with a different offer, then of course the details of who owns how much money is going to differ from one node to another, and then the nodes in our blockchain have broken consensus, and our blockchain is no longer usable. So in order to make our on-blockchain asset exchange usable, one node needs to be able to figure out exactly how to match offers with, say, buyers with sellers, or in general, given a set of input offers, every node needs to be able to come to this exact same conclusion about how money is transferred between players given these offers. Okay, so how can we do this? Well, it turns out that there are asset exchanges existing in current real-world blockchains. Things like Uniswap or Bancor on the Ethereum network, or the Stellar blockchain provides a native asset exchange. And the way that these asset exchanges achieve a replicable operation is by serializing transaction processing. In particular, they come up with a way of processing one transaction in a repeatable, replicable manner. And then they also agree on a fixed ordering for processing transactions. So for example, the blockchain might say that when they get a new offer to buy something, this offer gets matched with the lowest priced seller that is currently active in the market. And then they'll also agree on a fixed ordering. Typically, this ordering will be, the literal ordering that the bytes of transactions appear in a packet of data. But you could also imagine applying a pseudo-random or agreed upon but pseudo-random permutation to the transactions. And this is all fine, except that this means that transaction rate of the entire system is inherently limited by the CPU speed of one CPU core. If we ever want to bypass this bottleneck, we'll have to process transactions in parallel on multiple CPU cores. The problem, though, is that if we parallelize transaction processing, we inherently give up any ability to process transactions in a repeatable order. Simply put, different validator nodes are going to have different hardware configurations, and some are going to have some CPUs are going to be have contention with other background processes, and in general, the hardware thread scheduler is going to be something, from our point of view, a non-deterministic process. And so our main question then is there some way that we can come up with how to process individual transactions such that we don't need to process transactions in a serial order in order to achieve a replicable operation, or not, in order to achieve a replicable state change. Okay, so that's the scaling on-chain asset exchanges part of the title. The part of the title is the Debreu exchange market. So there's the Debreu exchange market is a model for the for a general economy dating back to the 1950s. And there's many variants on this model, but we're going to go with a simplified version, and that is we'll have some number of agents, and they're trading some number of different assets. Again, all assets are divisible and fungible. And at the start of the economy, every agent has some endowment. So for example, we might be trading dollars and euros, and one agent might have $3 and €2. Then the market produces a public set of prices, say. And these prices are denominated in a fake currency, say monopoly money. And every agent sees these same set of prices. Then, once they see the prices, they sell their entire endowment to the market in exchange for this monopoly money. I should point out that no agent's endowment contains monopoly money. They only get the monopoly money that they get from selling their endowment to the market. And finally, agents spend all of their monopoly money to buy whatever set of goods they desire most. Formally speaking, we'll say that every agent has some utility function, and they maximize this utility function subject to their budget constraint. And also, agents have no utility for this monopoly money. So for example, our agent had $3 and €2. He sells all of his endowment to the market and gets 7 monopoly money, and then spends that 7 monopoly money to buy back $5 and €1. And the critical point, part of this model is these prices. So we'll say that a set of prices is an equilibrium for an Debreu exchange market. If after all these agents go through this process, they sell their endowment and they buy back their desired set of goods, a set of prices is an equilibrium if for each good, the total amount of the asset that is sold to the market is equal to the total amount that is bought from the market. In other words, no assets are overbought or oversold. No assets are created out of thin air or destroyed. And every agent is able to buy from the market exactly what they want. Now, if you're familiar with the Debreu market literature, you'll notice that there's a couple of technical details around the definition of an equilibrium here that I'm eliding. We'll have to deal with those if we actually implement this in practice, but they don't change the big picture. So we'll think of, for the rest of the talk, we'll think of an equilibrium as uniquely specified by a set of prices. Okay, how can we power an asset exchange in the real world using an Debreu exchange market? Well, the first thing to be careful about is specifying how individuals will interact with our exchange. And for this talk, we'll think about individuals submitting what we call sell offers to the exchange. These are similar to what are often known as limit orders in financial markets. And these sell offers are offers to sell some number of units of one good, and they request payment in some different good, and they demand a minimum price. So for example, one agent might offer to sell $5, and they might demand at least €2 in exchange for each dollar. So it turns out that these sell offers correspond to agents in an Debreu market with linear utilities. And for example, if I publish an offer that demands at least €2 in exchange for each dollar, then essentially I'm saying that I value €2 is equal to $1. I value 2.1 euros more than $1, and I value 1.9 euros as less than $1. And I can express this with a very simple utility function. Simply put, my utility for a set of goods will be simply the number of dollars that I have plus 1/2 the number of euros that I have. And it turns out that an agent in an Debreu market with this type of utility function displays the same type of behavior as what you'd expect from a sell offer. Namely, the agent sells their endowment and buys back the good in question, if and only if the price is at least a minimum threshold. Okay, so to put this all together, run an asset exchange via an Debreu exchange market. Well, every round we'll gather some collection of sell offers. Then we'll correspond every sell offer to some virtual agent in an imaginary Debreu exchange market. We'll compute equilibrium prices in this Debreu exchange market. And finally, we'll take those prices, and then all offers we gathered will trade at those prices of the Debreu market. So for example, suppose we again offer to sell $5 in exchange for, if we can get at least €2 for every dollar. But this time the market decided that the price of $1 is actually equal to the price of €3. And so this makes us happy because instead of €2, we'll get €3 for every dollar. And so what we do is we sell all of our $5 and our sell offer gets back €15. Okay, to put this in a blockchain context, what we'll do is that say every block, the block producer will gather together a set of sell offers, and then they'll compute these approximately equilibrium prices. And finally, they'll output a block. And this block, importantly, has to include the set of offers and the market equilibrium prices. Of course, the rate at which any offer trades depends on, of course, that offer and also the market prices. And so in order for transaction processing to be replicable, every validator node in our blockchain has to see the same offers and the same prices at which to clear those offers. And of course, this introduces a little bit of overhead. Namely, every validator node that's not the producer has to check that the prices that are included in the block are actually approximately equilibrium prices. But it turns out that this is fairly straightforward and very easy. What's more difficult is how to actually compute market equilibrium prices in this Debreu market. And so I'll spend most of the rest of this talk talking about how to actually compute prices. But before I do, let's just outline some basic requirements we have for this price computation algorithm. We're going to run it on every block. And every block, we're targeting, say, making a block every, say, 5 seconds. And so this price computation algorithm needs to be able to run reliably in under 5 seconds, and well under 5 seconds. We might target this algorithm to run in under 1 second. And also, this price computation algorithm needs to be able to handle very large Debreu markets. So if we want to have our blockchain really scale to large numbers of offers, say we want to make it match, say, Visa network throughput. Visa network throughput peak is allegedly 50,000 transactions a second, and so our block producer, since our block happens every 5 seconds, we'll need our block to have a size of at least 250,000 orders. Maybe it has 500,000 orders, maybe it has 100,000 orders, but that kind of ballpark. But also, sell offers that don't clear in one round are going to persist until the next block and to see if the price changes more to their liking. And so the number of active offers on the exchange might well exceed this, might well exceed the number that are in any one block. In particular, we're going to target having a price computation algorithm that can handle markets of size 500,000 or 1 million or 2 million or more. Okay, so now before I go on though, suppose that we have that kind of reliable equilibrium price oracle. Why is this a good thing to do? And the main reason is that if we process transactions in this manner, then we can process transactions in parallel while still getting replicable results. In particular, there's no dependence on the ordering of transactions, because the only things that affect the results of processing one transaction are the parameters of that transaction and the market prices. And so this lets us evade that single CPU scheduling or performance bottleneck. On top of that, though, sort of independent of the computational benefits, running an asset exchange in this manner makes access to the market more equitable. In particular, every offer within one block sees the same market prices, and this means that as long as I know that I can get my data to the exchange before a block cutoff time, I'll see the same prices and I'll get the same terms for trading as everyone else. And this means that somebody who lives right next to the exchange and therefore has a sub-millisecond latency connection to the exchange gets the same terms for trading as someone who lives far away from the exchange and maybe doesn't have a fiber connection, and therefore has a much higher latency for communication with the exchange. And finally, running an exchange in this manner means there's no arbitrage within the system, and it gives better liquidity between lesser traded assets. And by no arbitrage, I mean, well, of course, there's going to be arbitrage between our system and other external exchanges. I mean that by no arbitrage, I mean that within one block, I can't benefit by say trading dollars for euros and also trading euros back for dollars. In particular, if I trade dollars for euros, they'll trade at some rate, and if I trade euros back for dollars in the same block, they'll trade at exactly the inverse of the rate that I got them for, and so everything cancels out, and I'm no better or worse off. And by better liquidity, I mean that well, suppose that I have some smaller used or lesser used currency, and I want to trade this for some other lesser used currency. Typically in the real world, I would have to, I couldn't trade directly because there aren't many people trading directly between these lesser used currencies. In the real world, I would probably have to sell the thing I have for dollars or euros, and then once I have the dollars, then trade those dollars for what I'm trying to get. And this works okay in the real world, but it does mean I have to send 2 transactions instead of 1. And it also means that while I'm holding those dollars, I'm exposed to risk in the fluctuation of the price of the dollar. And there was no real reason for me to have to take on that risk. And so running an exchange powered by an arrow-to-grow exchange market means that I can trade, essentially, I can always trade directly from any one asset to any other asset without taking on intermediate risk of holding intermediate assets. Okay, now on to the price computation. So it turns out that computing equilibrium prices in arrow-to-grow exchange markets is a well-studied problem in the theoretical literature. And for markets with linear utilities, there are three types of algorithms that will be relevant for us. I'll talk about 2 in this talk. The first is what's called Atonement. It's an iterative process. There's also a number of approaches based off of convex optimization, convex algorithms. And finally, there's a number of algorithms based on, the combinatorial algorithms based on analyzing network flows. However, all of these algorithms in the theoretical literature have a scaling problem. In particular, all of the theoretical algorithms run in time that is so-called polynomial in the size of the market. And for us, that means polynomial in the number of sell offers, the number of open offers. And of course, if you recall, we talked about having the number of offers be, say, 1 million or 2 million, some very large number. And so this is a problem. One thing to note, though, is that there are far more people in the world than there are types of asset. And concretely, we might think about people trading anywhere from a few dozen assets to 100 assets. Even Coinbase, one of the larger cryptocurrency exchanges, lists about 4,000 assets. And these are large numbers, but they're much smaller than, say, 100,000 to 1 million to 2 million to larger. And in general, an algorithm whose runtime is polynomial in the number of assets might be feasible, but certainly an algorithm whose runtime is polynomial in the number of open sell offers is definitely not going to be feasible. Our goal then is to come up with a way of transforming these theoretical algorithms from runtimes at polynomial in M to maybe polynomial in number of assets, or maybe with a log dependence on the number of open cell offers. Okay, so our first algorithm from the literature is what's called Atonement. It's an iterative algorithm, and simply put, we'll pick some candidate set of prices. And then at these prices, we'll compute total aggregate supply and demand. And of course, if demand is too high, then we raise the price. And if supply is too high, then we lower the price. And we repeat until we get to a market equilibrium. Now, every round of this process requires computing aggregate supply and demand at a set of prices. If we did this naively, we would have to iterate through all open offers, and of course, that's going to take time that's linear in the number of cell offers. However, one thing to point out is that the utilities of the agents in our Debreu markets, they're not arbitrary linear utilities. Agents only have valuations for two distinct goods. They only value what they sell and what they're trying to buy. So one thing we can do is to group agents by the goods that they value, and then we can sort agents by their minimum price. And with a little bit more pre-processing, then we can compute the total demand for a large group of agents with just one binary search. The intuition here is that if I demand a minimum price of, say, $5 per euro, and somebody else demands a minimum price of $6 per euro, well, if that somebody else is satisfied by market prices, then I have to be satisfied by market prices because 6 is less than 5. Okay, so this gives us a way of computing demand in time that's not linear m, but actually logarithmic in the number of cell offers. Now, another approach to solving the equilibrium problem comes from is a convex approach. So what I have on the screen here is a convex program. Don't try to look at this too hard. It's hard to parse. Just what I want to point out is that the objective is a summation over m. And so even computing the objective or taking a derivative is going to take time that's linear in the number of cell offers. Also, the beta I and yi that I've highlighted are variables, and these are indexed by different cell offers. And so the size of the convex program itself is going to be linear in the number of open cell offers. So a natural question is then, is there an efficient transformation of this convex program in the same way that we did for the Atonement process? And the answer is yes. However, applying that transformation means that the objective function of our program is no longer differentiable. And this makes it really hard for off-the-shelf convex solvers to attack the problem. So an open question, to which I would conjecture the answer is yes, but we don't know how, is there a more clever efficient transformation that somehow, again, breaks this poly-m dependence in the runtime that preserves differentiability or twice differentiability of the objective? Okay, so I've just spent some time talking about some theoretical algorithms, and I've claimed that doing certain transformations to them makes their runtime scale much better than linear in the number of cell offers. How do these actually work in practice? What I have here are plots of the runtimes of the unmodified convex program when given to an off-the-shelf commercial solver, and the average runtimes of Atonement, where we're averaging over trials where we generated a bunch of random offers and then run these algorithms. And I should point out two caveats first. One is that what I plotted here is just the runtimes of the algorithms, not anything else that we not anything else related to actually running an exchange. And two is that the absolute times are not comparable. Each algorithm measures error in slightly different units, and so it's a little bit like apples to oranges. What you should look at is the trends. The convex program has size that's linear in the number of offers, which is the bottom axis. And of course, as we'd expect, its runtime scales linearly as the number of offers increases. By contrast, the logarithmic demand oracle version of Atonement has only a logarithmic dependence on the number of offers. And so once there's a sufficiently large number of offers in the system, its runtime is actually essentially logarithmic in number of offers. Given this, once outside of very sparse markets, Atonement actually runs fast enough such that we could actually run it in every block. Remember, we were targeting having an algorithm that could run every block, and that meant an algorithm that could run reliably in under a second. And so if there are a large number of offers in the system, then Atonement runs reliably in under a second. And I should point out that also when in these sparse markets where Atonement doesn't work well, that's exactly when the convex program is small enough to solve. And I think the last takeaway from these graphs is that running that transformation of polynomial in M to logarithmic in M is a transformation that's critical to get real-world usability at the kind of large markets that we're looking at. So I'm running out of time, but those are some positive results. I'll just conclude with an impossibility result. So far, all of the operations that everyone submitted to the exchange were what we called sell offers. A natural extension might be what we call a buy offer. In particular, we might like to say, I would like to spend as few dollars as possible in order to acquire exactly 10 euros, instead of saying, I will sell $10 to get as many euros as possible. However, it turns out that as soon as we add buy offers to our system, then computing approximately equilibrium prices becomes p-pad complete. In other words, adding buy offers moved us from a very nice complexity class to a computationally intractable complexity class. Now, it's an open question as to whether or not some adversary could submit a bad set of buy offers to break the system. But yeah, adding buy offers makes the computational problem much, much harder. I'm running out of time, but just to conclude, I'll point out that we're constructing an Debreu, we're conducting an asset exchange, and we want to run it on a blockchain, and we want to run it at a very high transaction rate. And in order to do that, we need to parallelize transaction processing. It turns out we can parallelize transaction processing using the mathematical model known as the Debreu exchange market. However, using an Debreu exchange market to power an asset exchange requires being able to efficiently compute equilibrium prices in real time. And finally, we can get these efficient algorithms for price computation by combining insights from the theoretical literature with additional structure that's present in the real world problem. And with that, thanks for your time.
Great. Thank you. Very interesting result. We probably only have time for one quick question, but then during the general Q&A session for the entire session, if you're still here, we can answer more questions there. So one of the audience asked, can the logarithmic algorithm be extended to allow participants to have a value on more than 2 assets?
So the answer is maybe. It's not obvious how to do that. It becomes much more complicated because then if you have valuations on 2 different assets, it's hard. You can't. There's not like a linear order that you can then impose on open offers to trade.
Maybe that's a future work.
Yeah.
Okay. Great. Yeah, I have some questions, but maybe we should wait until the general Q&A. Thanks again.
Thanks.